Hello and welcome to the second Yorkshire branch webinar. My name is Chris Davis, Chair of the Yorkshire branch here at IHEEM and Deputy Director at Bradford Teaching Hospitals. Today's webinar will be presented by Martin Kenzie from 2G Energy, presenting hydrogen CHP systems. Martin supported by Alex Best, Head of Capital at Hull University Teaching Hospitals. For this webinar, we'll be using the Ask a Questions function to take questions from the audience. This can be found on the right-hand side of your screen and is the speech mark icon at the bottom of your screen. Please submit your questions through this function and our speaker will answer as many questions as there is time for at the end of the session. Finally, we request that no part of this webinar is reproduced and published in print or any other format. So I will now hand over to Martin. Thank you very much.
Thanks, Chris. This is our simple presentation that we've produced, and we've done this probably about 2 years now on the different hydrogen technology that we've got available, and the various projects that we've done and the applications of it that we've done over the last 9 years. So as I said, for us, this is nothing new in a certain way. This is just projects that we've done already and an explanation of obviously how we do it. So we're a German company. We're in the north of Germany, so we're based 9 million miles actually away from Holland. We've been in existence 25 years, and we're probably one of the large engine manufacturers not a lot of people have ever heard of. We produce probably about, I don't know, 500, 600 engines a year, and we produce them anything from 20 kilowatts all the way up to 1 megawatt for our own engines, and then obviously above 1 megawatt up to 4.5 megawatts. We have obviously distribution agreements with Yambacher and MTU and some of the other larger engine manufacturers. We're actually quite a heavy geared up research and development company in a certain way. We've got 650 employees, but 42 of them work in the research and development team. So we spend an awful lot of time, effort, obviously developing gas engines, which is obviously where the hydrogen development engines came from. And I can explain obviously a bit of the history about that. Where the sort of the current situation is for obviously hydrogen development and the hydrogen economy sort of developing, a lot of it stems from the fact that there's an awful lot of wind power being produced at the moment, which during the day is fantastic, but also at night there's a lot of wind curtailments where there's too much wind being produced and obviously not enough users to be able to take that power off. So an awful lot of work was being done to decide obviously how to utilise that excess sort of renewable energy that was available at night. So one of the great old technologies that sort of has existed quite an awful long time was electrolysis. So electrolysis is really just the splitting of water into hydrogen and oxygen. So a lot of the projects that we've worked on, or a majority of them, have electrolysis plants that's obviously connected to a wind farm, and obviously they generate hydrogen at night. A lot of the first phases of these projects were looking at obviously how to utilise the hydrogen that was being produced. And at that point, there was no sort of engines that could really run with hydrogen as a pure gas. So a lot of work then was being done in what's called methanization, which is effectively putting the carbon back onto the hydrogen so you could actually use it in gas applications. It seemed a bit of a crazy idea that you would take a completely renewable green gas and then put carbon back into it just to be able to utilise it. So about 12 years ago, something like that, the German government were trying to make a decision about which way they were going to put their economy, about whether to try and back the hydrogen economy or to back the battery economy. But obviously at that point in time, the Germans decided that they didn't really like where all the metals were coming from to make obviously all the battery storage. So the German government wholeheartedly decided to obviously back the German the hydrogen economy. So one of the initial projects that was done, which was Berlin Airport, and I've got more details on this later on, was done obviously to develop the hydrogen case study to prove that you could actually generate hydrogen from electrolysis using wind farms, the storage of it, etc., etc. But I'll cover that more later on, and obviously a detailed slide about that project. How this is actually works, and in a certain way, this isn't great rocket science or anything else. Utilising hydrogen is actually an awful lot easier than people think it is. For us, we just class it as it's a gas. We make gas engines. So in a normal conventional engine, you normally mix the air with the gas, or you obviously put it through a turbocharger, and then obviously you inject that turbocharged gas mixture into the engine, and obviously that drives it. what we found is when we were doing an awful lot of development on some of our syngas projects, a lot of syngas has got hydrogen content higher than 40%. And we found that because of the combustible nature of hydrogen, if you had a high percentage hydrogen gas mix, more than 40%, and you put it through a conventional gas mixer and into a turbocharger, you were running the risk of blowing the turbocharger up just because of the combustible nature of hydrogen. So for the syngas projects, what we found is that the best way to do it was actually to bypass the gas mixture from the turbocharger. And obviously that way we don't obviously get the problems obviously with the combusting in the turbocharger. So all effectively we do is we just put a gas injection system effectively just before the cylinder head of the engine. So what we do is, so with the air is still going through the turbocharger, we bypass the gas and we just inject the gas directly back into the airstream just before we put it into the cylinder. As I said, this was something that we developed for the syngas, the markets. So 10 years ago, when the German government decided that they wanted to trial and run an engine running 100% hydrogen, for us it wasn't really a great feat of engineering so much that we had the technology available already, the design for doing this. And effectively, all we did was we just played around with the compression ratios of the engine to be able to utilize hydrogen. So then 2012, it was, yeah, 2011, 2012, we did the first 100% hydrogen engine running 100% hydrogen. And I said for us, it's no great engineering feat in a certain way. I said for us, it's just a gas. It's just a technique that as long as you can bypass that turbocharger and just inject the gas. So a standard engine, we can run up to 40% hydrogen blend, above 40%. We put a gas injection system on it and we can run anything from 40% all the way up to 100%. So it's nothing exciting or sexy in a certain way. It's a gas engine. It's just a different type of gas that we put into it. So as you can see, obviously a lot of the times we still have the gas mixer built into the project or built onto the engine, and we obviously have the hydrogen injection system on it. What that means is obviously we can actually blend or take any sort of variable flows of gas. So we can run the engines on 100% natural gas or biogas, or we can run them 100% hydrogen, and effectively any sort of variance of those percentages of blends of gases in between. So once again, it's not really anything like a new technology or anything else. It's an existing engine that people understand. I said this is our standard engine. All it is effectively is with an injection system on it. One of the big advantages of this, because it's a standard engine, we can actually retrofit the kit, the injection, 20 of our engines that are actually in the fleet now. So you can actually have a natural gas engine that you've been running quite happily. And then obviously if you make the decision that you want to either have a demonstration project to have high percentages of hydrogen, or the natural gas is going to start getting hydrogen injected into it probably sometime later this year. So there's going to be more and more hydrogen available. At certain points in time, as soon as you decide that you want the engine running higher than a 40% blend of hydrogen, it's simple for us to come back to site, fit an injection system to it, play around with the turbocharger a little bit, and that's it. The engine that you've got doesn't need to be replaced, it doesn't need to be ripped out. It can just be retrofitted on site with obviously the hydrogen kit. So in essence, it's the key message that you can still run natural gas now, but you've got the ability that at some point over the operational life of that engine, you can get it running on hydrogen. Because I mean, most engines are lasting 15 or 20 years. So just a case is you don't have to throw something away that you've got, just retrofit it to make it work. So one of the big advantages also, which is also conversely one of the disadvantages of hydrogen, is quite combustible, which is obviously why we get the issues obviously with the turbocharger and the ability to bypass it. But one of the big advantages of the hydrogen is because it's so combustible, you can mix an awful lot of air into the gas mixture and still have it explode in the cylinder head. So obviously that determines obviously what the nitrous oxide, the NOx levels. So the operation window that we've got with hydrogen is a lot bigger than we have with obviously with biogases or natural gas. So what that means is as we can play around with the oxygen level that's obviously being injected into the engine, or the air level that's being injected into the engine, it also means we can lower the NOx levels down more and more and more. Initially, when we did the first project, I said 9 years ago, we were running the engine at 500 NOx, because obviously it was based on the biogas. type of specifications at that point. The latest version of the engines now we've got, still with the same power output and everything else, just by changing the air ratio, we're actually now running down at 95 knots. So once again, I said, hydrogen has got a lot of advantages over natural gas, just because of obviously the carbon position, but also the nitrous oxide position as well. And I said, it's for a gas, it's quite versatile for us to play around with. So once again, these aren't, I said, like blackboard calculations that we've done, and where we're saying what might be possible in the future. We have an entire range of these engines out. So effectively, all our engines can be converted to run on hydrogen. All the ones that we've got in the marketplace are obviously all based on our generator engine. So we've done everything from the 4-cylinder all the way up to the 20-cylinder, and all will run on natural gas, all will run on 100% hydrogen. I said it's a standard engine, just with a simple adoption of it to make it run on hydrogen. So once again, I said we've been delivering these projects, I said, for 9 years now. We've got them all over the place. Most of them are in Germany. We've got them in Dubai. We've got them in Japan. I said we've got the first one in Orkney Islands in the UK. We started on our 3rd series engine, which is why the one in Berlin Airport was our 3rd series. But obviously we're now onto our 4th series of engines. But once again, the development of the engine has always been based around obviously the fact that we can obviously make it run on hydrogen at any point in time. So this was the Berlin Airport case study. So this was the first project that was actually done on 100% hydrogen engine. And so it was a demonstration project that was done by the German government, just effectively to prove that you could have that, the economy of the wind farms, or the curtailments of the wind farm being used to generate hydrogen through an electrolysis plant, demonstrated the on-site storage of hydrogen. It also demonstrated the injection of hydrogen back into their gas grid, which is obviously now quite common in Germany. All the fleet vehicles on the airport were all going to be fuel cell vehicles. And obviously we put 2 engines on it to obviously demonstrate we can run engines on 100% hydrogen. So this is the actual engines. So once again, I said it's still got the gas mixer, it's still got the injection system on it. But I said, apart from the COVID, I said these are things you could go and kick this out and have a look around. I said it's nothing that just, I said, a case study that we produced thinking this was the future. I said we've been delivering these, I said, for a lot of years now. So once again, we see huge developments for this also in the district heating network. There's an awful lot of district heating schemes. They've obviously got CHP's engines on them to generate the heat and the power, obviously for the schemes. Once again, I said in Esslingen in Germany, they wanted to prove that you could obviously get a hydrogen generation system working. See, this is the Dubai one. So all of the projects that we've got in Germany are running on wind farms, obviously because they have huge wind curtailment in Europe. In Dubai, and also the ones we're looking at in Saudi at the moment now, their big advantage, they've got an awful lot of sun, and obviously they've got an awful lot of PV installations. So once again, it was done to prove that you could actually generate hydrogen, obviously from a PV. This was originally for the Hydrogen Expo, or the World Expo that was going to be last year, but obviously that got cancelled. But once again, all the infrastructure was still built up, so the entire expo was going to be hydrogen. All the buses and everything were going to be fuel cell buses. But once again, it just proves that the Middle East are looking at hydrogen generation in a really serious way, because obviously they can see the sort of like the end of sight where the petrochem industry is going to sort of die, and they're viewing at the moment now obviously to move into a hydrogen generation economy, because they've got all the infrastructure to be able to transport gases all around the world. And effectively, all you need is sunshine and water, and you can produce hydrogen. This is one of the projects that we won an awful lot of the design awards for, and the CHP awards, and et cetera, et cetera, et cetera. So this is the Habsford District Energy Scheme in Bavaria. So Bavarian town, it actually developed a strategy where they wanted to be completely 100% zero carbon. So they built massive wind farms to obviously power up the community and everything else. But it got to the stage where they've actually built 200% more wind power than you actually need. And so a lot of that was obviously being curtailed at night. So we'd already had the CHPs on there running on natural gas that was powering the school and the swimming pools, et cetera, et cetera. So once again, it seems to be an evidence development of the project to actually start generating hydrogen at night. So initially they were generating hydrogen and they were putting it back onto the gas grid. They were actually selling all their, most of their hydrogen actually to Greenpeace. So Greenpeace were buying all their effectively green gas credentials, obviously from the hydrogen that was being injected from the system. So once again, it seemed to be the fact that they had an awful lot of hydrogen. They had CHPs on there already, so it just seemed to be a natural progression. And obviously we put a hydrogen CHP on there as well. And obviously that works in conjunction, obviously, with the natural gas one that we've got as well. So once again, this was the Eslington district heating scheme. Once again, it was a demonstration project to prove that it didn't get district heating schemes running on 100% hydrogen. And once again, I said it wasn't too much of a case study to prove, because once again, we already knew CHPs are running on an awful lot of district heating schemes. And effectively, I said it's just changing the gas. Change the gas, you make it 100% green. It's not that hard, and the concept's very easy to understand. People are comfortable with what CHPs are in district heating schemes, or even said universities, hospitals and everything else. So it's not a new technology, it's just the same technology, it's just a different gas going into it. So this is Kirkwall Airport up in Orkney Islands. This will be, in fact, this is going to be on site in the next couple of weeks. This is the UK's first 100% hydrogen engine. Once again, this is a slightly different project from the others. This is the first project we've done where the hydrogen isn't being produced on site. So this was being part of the European Marine Energy Centre. So they do an awful lot of testing of the tidal turbines up in the Orkney Islands, because the tidal streams up there are quite good for testing tidal turbines. The interconnectors back to the Scottish mainland were quite weak, and so it was stopping the development of more and more of the testing tidal systems out there. So what they do now is they've got a large, I think it's an ITP power electrolyzer on E-Day. So all of the tidal turbines feed their power into E-Day. E-Day produces hydrogen, and then obviously the hydrogen is then getting obviously shipped from E-Day up to Orkney Airport in containerised storage tanks for us to use on the airport. So it's the first project we've done, I said, where hydrogen is actually being delivered to the site as opposed to being generated on site. So one of the things about this is at the moment, and why there's probably only said a handful of projects that have been delivered so far. At the moment, the economics of this don't work out. Even with the electrolyzers and everything else, it's probably costing about 12p a kilowatt to generate a kilowatt of hydrogen, compared to about 1.6p for natural gas. So at the moment, it's not economic to run a project on hydrogen. I'm quite honest about this. All the projects we've done so far have effectively either been grant funded or they've been Pathfinder projects to demonstrate that the technology works together, as opposed to generating a financial business case. But hopefully later this year, BEIS are going to be doing the announcements probably on CFDs, contracts of difference from hydrogen generation from electrolysis. So obviously everyone's looking about obviously what that will do to the cost of hydrogen, with obviously a subsidy being applied to it. So everyone's just expecting obviously that the cost of that generated hydrogen will start falling over the next couple of years. It says CO2 abatement tons there, because when I wrote this presentation 2 years ago, no one was really certain about how the sort of renewable incentives can get placed on it, and we knew at the time that the Dutch government were placing huge subsidies on their carbon abatement from electrolysis, so that's why there's a CO2 abatement figure there as well. But I mean, you only really need hydrogen to drop down to about 5.5p a kilowatt for it to start making an economic break-even point. I said it's 12 at the moment based on the S&P hydrogen pricing. But as I said, it's only got to come down to 5.5p for it to break even. Below that, all of a sudden you're eating into then an economic case for actually generating hydrogen on site or utilising hydrogen and making the whole thing completely green and an economic business case. So once again, I said there's going to be some sort of point when, because of the economic conditions and the utilisation and the figures of payback, where running on natural gas, there will come a conversion point when all of a sudden it makes sense to convert those engines to run on hydrogen, whether because hydrogen's available on the gas grid or whether because the economic conditions are ready to either have hydrogen shipped in or to generate hydrogen locally on site. So I said it's just a case of watching and waiting, and it's like everything. When the first PVs, solar, wind farms, when everything first got built, nothing was economic. But then all of a sudden you reach a stage where, because of the subsidies, people start kickstarting the industry, and then obviously with massive volume, obviously the prices drop down, and then it becomes more economic in the same way that you can do wind now with actually any subsidies at all. One of the things that's also most notable is people think there's a direct correlation between the amount of hydrogen you're injecting into a system and obviously the CO2 reduction. So obviously everyone has this feeling based on obviously the Keele University project that the gas grid's going to go up to a 20% hydrogen blend in the next couple of years, whether it's 6-7 years, etc. I'm thinking obviously that's going to produce a 20% drop in the carbon reduction. But it doesn't, because of the calorific difference between hydrogen and natural gas. If you have 20% volume of hydrogen on the gas grid, it only actually gives you about 8% carbon reduction, obviously because of the calorific differences. So once again, it's one of these facts that as you start getting into higher and higher percentages, it starts really, really eating into obviously the carbon and the CO2 reduction all the way down to obviously the 100% when it is completely green. But obviously at the lower levels, it's not impacting as much the CO2 target as people think it is. It's why we know a lot of people that want to make massive carbon reductions and carbon statements effectively will need to have self-generated hydrogen on site or hydrogen deliveries on site. I mean, at some point, obviously, in the next 20, 30, 40 years, the entire gas grid will go hydrogen 100%. But it's a case of when you want to make that sort of move and how much, obviously, CO2 reduction you want. I mean, it's quite easy to back calculate. If you want X amount of CO2 reduction, you need so much hydrogen going into your gas mix to produce it. And I said, everything's possible. So once again, I said hydrogen is, I said it's one of the big advantages we've got of engines, because a lot of people have the conversation engines or fuel cells. One of the big advantages of the engines, because they're designed for syngases and biogases and everything else, we don't need 100% pure hydrogen to go into it. We can have a little bit of impurities into the gas stream, unlike a fuel cell. I mean, a fuel cell needs 99.999% pure hydrogen. The engine doesn't. We can use hydrogen as a byproduct of other processes or anything else. We can also do obviously step loading on the engine. A fuel cell wants to obviously switch on and run 100% whack full all the time. We can modulate an engine up and down, no problem at all. I mean, it is what we do already now. We load, follow electrical demands on sites. And because I said it's existing technology, these things fitting into island mode operations or virtual power plants, it's all easy. It's all been done already. I said, this is nothing new. I said, it's a standard engine just with a bit of kit on it. And once again, the possibility of doing mixed gas into the engine. I mean, it's like some of the projects we've done so far. I mean, like Hapsford, if they still want to run their engine and they haven't got enough hydrogen, you can put natural gas into the engine if they still want heat going into the swimming pool. So once again, it just gives you a great deal of viability of how you can play around with the running of the engine. So where does this all tie in with the NHS and everything else? Well, one of the big advantages, and once again, it's one of these strange things that's come about in the last couple of years. All of the hydrogen that we use is obviously generated from electrolysis plants, splitting the water, hydrogen and oxygen, where we always wanted the hydrogen. And in a certain point of view, obviously the oxygen was seen as a sort of the byproduct or the waste as it is. But then obviously a lot of discussions that we've had obviously with the NHS and some of the water boards, the oxygen is obviously a really usable commodity. And then obviously because of COVID and everything else, oxygen usage in the NHS went through the roof. So then all of a sudden, the idea of having a localized electrolysis plant on a hospital seemed obviously very viable, because obviously the electrolysis plant can produce obviously hydrogen, it can go into the engine, the oxygen can go into the hospital. But I think that's where I am basically. As I said, it's only a simple, quick presentation on the hydrogen technology and what's available. And I said it's engines people have already got. I said it's not a new technology. It's a gas engine that we just make to run on a different gas. Simple. That's it basically.
Thanks for that, Martin. Alex, do you want to come in now and just share some share some thoughts and experience on the subject?
Yep, thanks, Martin. We've as a site, we've got two main acute sites. and we have a smaller offsite, and we have the 2G engines with 100 kilowatt on our sterile services unit and a 1.5 megawatt at Hull Royal Infirmary, and soon to be another 1.5 megawatt at Castle Hill. So we, admittedly, like many other trusts over the last 5 years, we've been looking at CHPs, and if not longer, with the CEF, before we decided to go alone and fit it and install it ourselves. CHPs were there for an economic reason for us as a trust, but as many other trusts, we've been successful in PSDS funding this year, primarily for decarbonisation, and that really ties that into our green agenda and our green plan and how we decarbonise our estate over the site. So we're just at the start of our campaign really of how we decarbonise both sites with heat pumps and reducing our electrical demand. But one of our key elements is we'll get so far with changing all our independent gas boilers for heat pumps, but on both sites we will have two rather large CHPs, notwithstanding our smaller unit, that make up a significant contribution of our gas emissions or our gas consumption. So the ability to decarbonise our CHPs is a real winner for us, and especially as we installed our 100 kilowatt and our 1.5 megawatt unit at Hull Royal. They were installed around about March last year, came online at Hull Royal in May, and April for SSU, and our next unit's due in probably more than likely August when we come online. To us, these are long-term assets, these CHPs. They're 15 years lifespan we're hoping to get out of the unit. So when we tie that into our green agenda, which we're hoping to be certainly our scope 1 and scope 2 emissions by 2030, to be looking to reduce those to zero, at some point in time we've got to tackle the elephant in the room that is our 2 CHPs and smaller unit of sites. That's really where we're looking. And if I'm perfectly honest, when we purchased these units, hydrogen was never a consideration, nor was the green agenda or decarbonising our estates. That was the infancy really before PSD started releasing their funding. So 2G was never really, we never selected 2G on the basis of hydrogen and the ability to do so. But what we probably did select them on was, and one of the elements was their ability to innovate. So we are putting some elements in that not necessarily being supplied by 2G, but such as CPCs. We've got one of those being installed by Spirit Sarco. That should hopefully come online in October. So we look to use our waste heat from the unit, and it's, to me, the hydrogen is a natural evolution of how we optimise and utilise our CHPs in the most effective manner and use them as long-term assets. We've looked into electrolysis plants, and as Martin said, they're at the minute they're significantly some significant costs really for the electrolyzer plants, and we've never really had the technology to support it. So, for example, I think when I last spoke with Martin, the equivalent power consumption for an electrolyzer plant to generate the amount of hydrogen we require for one of our 1.5 megawatt units is about 4 megawatts of electricity. So it's the economics doesn't stack up for us to put that much electricity into a hydrolyzer to generate the hydrogen. But one of the benefits of the PSDS schemes that we've gone down the route of is we're actually putting quite a large PV array on one of our adjacent to Castle Hill site, which is ironically about 5 megawatts, which would provide, if we went down that route in the future, enough power to generate sufficient hydrogen to run our unit at Castle Hill. So it's we're starting to get the elements in of how we could possibly decarbonise our CHPs. So hopefully that provides some context, Chris, to where our approach and how we've been working with 2G. And I think we're not unique. The technology we're looking at and the options could certainly be used by every other NHS trust across the land.
Yeah, thanks for that, Alex. And thank you, Martin, for presenting that slide deck. Thank you very much. Just in terms of questions, I don't think we've received any questions yet, but if anyone's got a question, please post them in the questions function, please. I think we've just received one. Bear bear with us.
One of the interesting things as well, one of the other NHS trusts that we're speaking to as well, because obviously this idea of obviously where do you get the power from to obviously generate the green hydrogen. And I know that they're looking at maybe acquiring a large wind farm or a stake in a large wind farm, and then effectively get a sleeve-in contract to obviously get the electricity to the site to obviously do the hydrogen generation.
Yeah, thanks, Mark. We've got a question. I can't quite see who's asked it. I'll just read the question out. Was the energy output is equally split between electrical and thermal? Bear with us, sorry. Just trying to get... Just having a few issues with the my dashboard. Bear with us.
Hi, Chris, it's Gemma. Would you like me to read the question out for you?
If you want, Gemma, I'm just having a few issues.
So a question from Stephen Bishop. It's as the energy output is equally split between electrical and thermal, I'm interested in how you utilise the thermal output and what, if any, decisions this has led to on site. Does this reduce the time pressure on cutting site thermal demand?
Is that
Martin, or...
Well, as I said, the CHP, I mean, obviously, in all utilisations, we try to generate, it's right, we generate roughly the same amount of electricity and we do with heat. It's utilising the heat as well. That is obviously one of the major keys for this. But it's why the hospitals have always been great applications for CHP. Hospitals use an awful lot of heat. So obviously the great advantage of big CHPs is it can generate all of the electricity, or as much electricity as the hospital requires, and effectively as much heat as they can take.
Thanks for that, Martin. And Gemma, can you still help us out on them questions, please?
Yeah, of course.
Cheers.
Okay, so we've got a few questions coming in from Russell Greenwood. The first is, what is the embodied carbon of the nitrogen conversion kit? Who's best?
Guess these questions are for you,
Martin. Conversion kit. We don't have one because, as I said, when we play around with the engine, lowering down the nitrous oxide in the engine is actually just it's just an air fuel ratio. The amount of air that we can put into the gas mix and still have it blow up inside the cylinder head when we obviously put the spark plug ignition on it. But that's the advantage with hydrogen. Because it's so combustible, we can put an awful lot of air into it and still get it blowing up, which is obviously why we can lower the NOx levels down, even without doing SCR, catalytic reduction, or anything else. We can achieve 95 NOx and probably even lower, just playing around with the air fuel ratio. So it's not a piece of equipment that we put onto it. It's just playing around with the air fuel ratio, the compression ratios in the engine. Because, I mean, conversely as well, it's one of those other strange things. Before we started talking about the utilisation of the oxygen output of electrolyzers into hospitals or like the wastewater treatment sites, we've also done a lot of development about putting the oxygen actually into the engine itself. Because obviously if we run the oxygen or the engine on pure oxygen as opposed to atmospheric air, there's no nitrogen compound in it, so we can effectively get an engine where we don't generate any NOx at all.
Okay. Another one from Russell. You might have already answered this question, so let me know if you have. If you are shipping nitrogen, what's the embodied carbon of that? Or is that already been answered? Sorry if it has.
We're not shipping nitrogen.
Oh, okay, there we go. Okay, let's see. Another question from Mick Cockshot. Are there any major safety concerns with on-site storage of hydrogen specific to a hospital?
I mean, in reality, I mean, all the projects we've done, I said, apart from Orkney, all have on-site hydrogen storage. I mean, hydrogen is not a new gas. I mean, if you go to BOC or Linde or any of these, they'll give you hydrogen storage vessels. I mean, hydrogen's, I mean, millions of tons of it are used every year in industry. I mean, there's hydrogen being stored everywhere. I mean, in the Hapsford project, which I said is effectively a scheme in a town. You can probably see in the picture, the hydrogen storage tank is actually behind the engine.
Okay. We've got one from Peter Chapman. Is there scope for steam waste heat boilers on the flue of a H2 CHP?
Yes. I mean, it's like, I mean, a lot of the hospitals actually, we generate steam from the CHP, probably in hospitals more than we do low temperature hot water. We put a waste heat recovery boiler on the exhaust outputs for the engine. It's quite common how we play around, and in the hospitals and also in industry, we generate more steam than we actually do low temperature hot water.
And that's the exact setup for both of our engines, both on steam waste heat boilers. The LTHW one, we've actually put in, we use it for a local ward on our ICU at Hull Royal. At Castle Hill, we'll be using it again for some localised buildings. But when I mentioned about the CPC, that's because we use it for domestic hot water to one of our ICU buildings. We will be using a CPC, which will convert that waste heat again to additional electricity.
Okay, thanks guys. I have one more question at the moment, so if there's any more, pop them in now. It is, how does increasing the air / fuel ration affect the engine output power?
For hydrogen, not a lot. I mean, this is one of the things, what's called the control window. Normally on natural gas or biogases, if we start playing around with the air fuel ratio to lower the NOx down, it's what happened a couple of years ago when the medium combustion plant directive came in, and the natural levels of NOx had to be lowered down. It did affect obviously the mechanical output and the electrical outputs of the engine. It's not so effective on hydrogen, just because it blows up quite easily. With natural gas and a lot of gases, it does have an effect. If you try and lower a normal engine from 500 NOx or what used to be 4,000 down to 95 milligram NOx, it will have a power derate on the engine. You don't really get that on hydrogen.
Okay. Russell's just put in some clarification on his question. So he said, if you are suggesting the technology can be low or zero carbon, then it's not just in operation but whole life, including manufacturing. How has this been considered?
I haven't considered it. I'm not too sure how they consider it from wind turbines either.
Okay, I've got one more question in from Stephen Bishop. When sizing a CHP, which is more important, let me reword that. When sizing a CHP, which is more important to match closely, site electrical load or site thermal load?
Electricity. The cash is always in the electricity. The electricity is worth 6 times more than the heat.
Okay.
Yeah, we followed that exact approach for both our sites. Our units are sized to meet our base load. Obviously, with different sites, Hull Royal, we can use all of our thermal waste heat. Castle Hill slightly different, but yeah, it's an economic reason why we've installed them.
Okay, I have run to the end of the questions from the audience at the moment. Oh no, another one's popped in as I've just said that, so I'll go with that one. So someone said, if you don't already have a CHP, what are the benefits of combusting hydrogen over using it in a fuel cell? Wouldn't combining a fuel cell and heat pump produce more heat?
The cost of a fuel cell and the maintenance and running of it outweighs it. That's why, I mean, one of our customers is actually one of the biggest fuel cell manufacturers in the world, and they buy engines for their projects. It's because of the capital cost difference in them and also the maintenance costs. But it's also the variable loading that you can put on an engine compared to on a fuel cell. But it's also one of the natural things. As I said, a fuel cell needs what's called 5 nines, 99.999% pure hydrogen. An engine doesn't. So if you're buying an electrolyzer that needs to produce medical grade hydrogen, it's an awful lot more expensive than if you just get one producing 99% hydrogen.
Okay, now I have actually reached the end of the questions. So I think I'll probably hand back over to Chris now.
Yeah, thanks for that, Gemma. Yeah, we'll just wrap up now. And so yeah, thanks Gemma again for helping out with them questions. And thank you again to our speakers, Alex Best, Head of Capitol Hill University Teaching Hospitals, and a big thank you, Martin, for for sharing that presentation today. And thank you to all for watching this Yorkshire Branch IHEEM webinar. Thank you and goodbye.